passive dynamic walking. So imagine a ramp and I purposely drew it at a slope. Okay, that's one leg. The other leg is, let me draw it in a different color. Okay, now I need to start somewhere. So I'll assume that this is the phase where one of the legs, the black leg, hits the ground, and what I'll call as the foot strike. Now this one doesn't have a foot like we do, but it's just a point foot. You can add more links to it to make it look like a human, but that just complicates life. The moment the black leg or the front leg hits the ground, we will assume that the rear leg leaves the ground. Now, this is not true for humans. When the front foot hits the ground, the back leg doesn't leave the ground immediately. There's a phase when both legs are on the ground. That's known as a double stance phase. Here we assume there's no double stance phase. So we just started with that. Let's keep going. So this is like taking snapshots of the robot at different instances to see what the motion would look like. So now the red leg is airborne and it is swinging in front. And we'll use this terminology where we'll call this the swing leg, and we'll call the other leg the stance leg. Okay, so then go this way. Okay, so the swing leg keeps moving. It eventually ends up in front. And then the final step is when the red leg, or the one which was a swing leg, hits the ground and becomes the new stance leg. So let's draw that in red. And then the trailing leg now is the black leg. And this is, again, foot strike. And the moment that happens, we'll assume that this foot will release, and then we'll have continual motion. Okay, so here, let's call this, let's say 1, 2, 3, 4. So 1 to 2 to 3, 4. You can see that 1 is the same as 2. This is equal to, sorry, 1 is equal to same as 4, not 2. So we can see that we can call this as one step. And if you want to make multiple steps, you just repeat that. So as long as we can model this one step, the way I've shown, we can just make this go forever, right? Assuming it doesn't fall. Okay, so for the bouncing ball, we identified a free fall and a bounce. In this case, what we'll do is we'll give these names. We'll call this phase when one leg is on the ground as single stance. What happens single stance is one leg is on the ground, other leg swings. At some point of time, you need to detect the ground, which is basically that red leg, which I showed, has to be, we keep checking when it's going to, when the distance or the height of that leg from the ground, or the vertical height, or you can also use the height against in the direction of perpendicular to the ramp becomes 0. And that happens, we have detected the ground. Once we do that, we will model foot strike. And then it just keeps going on. So this is our one step. Okay, so clearly after foot strike, we'll also have here we should write single stance, and here I should put foot strike. Okay, so keeps happening, but we just want to model one step now. So it's clear that we need to write the equations for this. We need to write the equations for foot strike, and then we need to write the equations for detecting the ground, which is actually it's just a geometric condition. When the foot hits the ground, the height is 0, right? So we'll try to write the equations for single stance, for foot strike, in detecting the ground. And once we have that, we are in a stage to then do the simulation, and then to aid in understanding, we'll also do an animation. So we'll start doing 1, 2, and 3. Okay, so let's get to that. 1, equations of single stance. Okay, now these equations are going to be very similar to that of a double pendulum, but there's going to be a difference in the sense that for a double pendulum, when we modeled it, we had 2 pin joints, one for the first link, another one between the 2 links, and it is to just move around that. Here, what we want to achieve is we want to continuously detach the leg from the ground and reattach it, right? So what we'll do is we'll use what is known as a floating base method to write the equations, and it will become clear in just a bit. First, let's try to put the model parameters. So I'm going to write the equations such that, well, let's call this θ1 and call this θ2. Now I'm using a slightly different convention as I use for a double pendulum, and this is just to make it convenient for me to then do perhaps control. So θ2, normally, if you look back to a double pendulum, I usually take, just pull that up. So if you look at the double pendulum, right here. Okay, so the way I define the angle, so this is how a double pendulum looks, and the way I've defined the angles is, it's basically the angle between this leg and then this one. Can you see my cursor here? So it's this angle, θ2, right? I chose that because that was the most straightforward way for me to write the equations. But in this case, I'm trying to make it more convenient for myself to do control later on. And so what I do is I just choose it to be the way it is. And then we'll figure out what the right angle is when we use our frames to take care of the fact that it is not the straightforward angles we wrote down for the double pendulum. I'll define a few more key points which would help me to write the equations. Let's call this point, which is on the ground or the foot, point foot, as C1, the other foot as C2. Just we'll make a generic mass distribution. So we'll just assume that there is, the legs have some mass M1, but I call them M, and then the legs have inertia I. And there's no reason you need to have the same masses. Just I just made the legs symmetric just to make it easy to write the equations, so the equations become quite big. And then we'll assume that there is a point mass on the joint between connecting the 2 legs. So this is something which people do all the time, which is if you want to model the upper body, you could have a link and then put a mass inertia but they try to model the upper body as a point mass. So M, capital M is your upper body. And when you walk, normally you don't really move your torso a whole lot, right? So the inertia effects is, we can just ignore the inertia effect. And that's the justification why we don't want to have an upper body with inertia. It also makes the equations complicated. So one thing you could do is you could do this analysis and then go to adding an upper body with a mass and inertia. Okay, so now we got that. Let's put a few more variables, a few more key points. Let's call this point G1, where the center of mass is for link 1, G2 for the one, and then let's call this H. And I'm just doing that because we will be interested in finding the positions of them for the Euler-Lagrange equations. Okay, and then gravity is, okay, so all my figures I showed the ramp as sloping downwards. Here I'm going to use this trick, which is instead of making the ramp at an angle, the way I've shown it in the previous figures, I will actually rotate gravity. So my ramp is now flat, but gravity is rotated. So the gravity is, this is the slope. And then gravity is, you always know, is all, so this is my ground. And gravity should point normal to the ground, right? So this is just done to make it convenient. When I write the equations, you'll see that the equations are much easier to write, assuming that the axis or my world frame is along the ramp and not along the ground. And that can be achieved by just rotating gravity. So gravity here would be G, this would be gamma, so G sine gamma. And this would be G cosine gamma. It just makes my life easy. I can just rotate gravity instead of doing it the other way where I have the axis along the floor. Okay, to think with that, I'm all set. Let's try to think of equations of motion. So I'm going to follow the same recipe. Compute positions, compute velocities, write the Lagrangian, write the Euler-Lagrange equations to get the equations of motion. And you'll see that the first step is the most critical one. The step 2, which is Lagrangian and the equations of motion, are, I just used a computer to do them. I won't really even try to get those equations because they're very lengthy. So let's compute the positions of points of interest. And I think positions of interest are C1, G1, H, and C2. So A, positions, velocity. Okay, now before I can write positions, I need to fix frames, right? That's the thing we've been always doing. So let's fix frames, and then we'll use that to write the equations. Yeah. Yes. G, this is gamma, better. Okay, so x0, y0 is some point along this along the slope. Okay. Now let's start putting frames. This is my link 1, and that's my link 2. So what I'm going to do is the easiest, and this is something you realize, you can put x1 along any way you want. You can put x1 this way, you can put it this way. It's your call. It doesn't really matter. It's taken care when you actually write the angles. So in this case, as I've been always doing, I'll always try to write the x1 along one of the legs. It just makes my life easy when I write the position of points. And remember that z always points out of the plane. So you have to follow the right-hand rule. So x cross y is z. And you can only get x cross y equals z in the right way if you have y pointing that way. So if you curl your fingers to right fingers of your right hand from x1 to y1, your thumb gives the direction of z, and it's pointing out of the plane, that means that you got it right. Okay, and let's do the same thing for this one. Let's draw x2 along this. And if you have y2 along the normal, then again, if you curl your fingers from x2 to y2, your thumb gives the direction of z, and that points out of the plane. It means that you got it right. Okay, I think that's pretty much what we need. Let's try to fill in the angles. Theta1 and theta2. This is something which I wrote rest from there, that figure. Okay, so we have all the frames. Let's try to identify or give some coordinates. So this point, C1, as you know, as you take multiple steps, this point C1 will keep going forward, right? It is not like a double pendulum with a fixed pin joint where it's always at the origin, keeps moving. So we just assign it x comma y. Then, given this x comma y, we can compute the positions of these points just by using our frame. So let's do that. Before I do that, if you recollect from here, we wrote theta1 as the angle between x, x. Okay, I just wrote it between x1 and y0. And I think this one was x2. This one was x2 and x1. So I try to write the angles as the ones between consecutive x-axis, and that just makes it easy to write the equation. So what I'll do is, let's just go there and do the same thing here. Okay, so we have that as theta1. We want to compute the angle between x0 and x1, because that is the one which figure out in the rotation matrix. So let's compute this angle. Okay, so you can see that that is 90 degrees. This angle is 90 degrees, and this angle has to be the same as this one, theta1. So the angle made between x0 and x1 is 90 plus theta1. So it's 90 plus theta1. That's the angle between x0 and x1. We would also need the angle between x1 and x2. This line is x1. I just drew it there so that I can then compute the angle between x1 and x2. So we need to compute this angle. Okay, so that you can see is nothing but 180 minus theta2, right? Okay, now there's one thing which you should be mindful of, which is we need to draw. I just drew the angle, but I did not really put an arrow to the angle. It's very important that we write the angle in the right way. The angle is always between x0 and x1. So if you have x0, which is this way, and x1 pointing as shown, then the angle is always from the lower index, which is 0 to 1. So it's from x0 to x1. And that is considered the positive angle. And so I have that in the right way there. So it's 90 plus theta1. We have to do something similar here, which is I need to go from x1 to x2. And that is my correct angle. And you can see that that angle is not 180 minus theta2. It is actually minus of that. This angle is 180 minus theta2. But this angle is negative of this. So let me just remove this, it'll be confusing. This is theta2 minus 180. Just because of the way the angle is shown. Now, another way to think of it is, if you want to change the direction of this arrow, you want to point it the other way, which is pointing this way. then you'll have to do negative of theta 2 minus 180. So 180 minus theta 2. And then if you add theta 2, you get 180, which is the right angle, right? The angle all the way is 180. So that's how you can check. So the angle between x1 and x2 is theta 2 minus 180. Okay, so with that, we can now try to write the position of different points. Remember, we need the homogeneous matrix, and that's why I was writing all these things. So we have R10 is cosine of 90 plus theta 1 minus sine 90 plus theta 1, sine 90 plus theta 1, cosine 90 plus theta 1. R21, I just have to swap this with the angle I wrote for theta 2, which is cosine theta 2 minus 180 minus sine theta 2 minus 180. And cosine okay. I would also need the positions of frame 1 with respect to frame 0. You can check that here. This is this point is O1 with respect to frame 0, and you can see that it is simply x, y1. We write 1 because of the homogeneous matrix. So x, y1. Then we want the location of this point. This point is O21. Okay, and that is, remember, it is the position of that point with respect to the local frame x1. This is the local frame. So the position of that point is, I need to specify some length. Let's call this L. And then I should have put it here. Say the leg length is L, and then this distance is C. So the distance is L. So it's the distance along the frame 1 is L along x1, it's 0 along y1, and then just a filler so that we can do the homogeneous calculation. So we have that, and I'll just transfer this to the next page. X, y1, L0, 1. Okay, so now we are all set. Let's compute the positions of, 5 points. I would compute the position of H, G1, C1, G2, C2. Because I need them later on for the Euler-Lagrange equations. Okay, C1 is simply O1 with respect to 0. C1 in frame 0 is simply O1 with respect to frame 0. That's very trivial. C2, sorry, let's go to G1 actually. Okay, G1 is going to be H10 times G1 with respect to frame 1, right? So what's G1? Let me just fill this up first. H10 is R10, O10, 01. And then G1 in frame 1, if you look at this figure, you want to compute the position of G1 in frame 1. Okay. And you can see that this point is along X1 axis. So it only have an X coordinate. That's the first thing. Second thing is the distance from the origin, which is right here, is going to be the length minus C. So L minus C is going to be the position of that point from the point C1 or O10. So what I need to do here is it says L1 minus C01. Okay, then I have H with respect to frame 0. H is the point which I call the hip or the torso. You can see it's along the X1 axis. It's going to have exactly the same things as G1, except that the distance from C1 is going to be L. So just to be complete, let me write this as, this is actually a bad notation. I shouldn't have used H because it confuses with H10. Let me just change the name. Let's call it something else. We just call it T is, let's call it P. Okay, so it's not confusing with H, which happens to be our homogeneous matrix. So let's call it P. Okay, so P with respect to frame 0 is H10, P with respect to frame 1. And then I said it's L01. Okay, so we're done with 3. Let's finish up with C2 and G2. Okay, G2 with respect to frame 0 is H2 with respect to frame 0, G2 with respect to frame 2. You know, I took a shortcut. I did not really write it as H10 times H21. Just wrote it in one step. H10, H21, G22, R10, O10, 01, R21, O21, 01, and then G2 in frame 2. Okay, it's always easy to write. When you see the same index, it's usually very easy to write it. You can just see it from the figure. We need to find location of G2 in frame 2. Frame 2 is right here. And so it's the location of G2 from the origin, which is that point P, is simply C. So we have C01. Okay, and the last point is C2 with respect to frame 0, H20, C2, frame 2. The only difference being now is that it will be at a distance of L instead of C. Everything will be the same. So R10, 0, O10. Okay, so I will not simplify that. I'll just line simpy to simplify all those equations. But I need this so that I can write it in as Python code. Okay, now as I mentioned briefly that what is known as a floating base, and the floating base is something which can move. In this case, we have a floating base because the point C1 is here, is not fixed. It is floating. We attach x comma y to it, and as the legate or the passive walker moves, that point will keep changing. In fact, it will change discretely. Once it takes a step of length L, it will become L comma 0. Then the next step will become 2L comma 0, 3L comma 0, and so on. So that's the floating based. And it's done in that fashion is because it makes writing equations. It's a bit more to develop the equations, but once you do it, it's kind of easy to keep track of the point C1 and then use that to do simulation as well as animation. So this is what gives it the name floating base. Floating base. X, Y. Every step. You know, one more thing which I forgot to do, and I should probably do before we get into equations, is I have actually rotated gravity. Okay, so one way you can do is you can use G sine gamma, G cosine gamma. It's one way to do it. Other way to do it is to actually figure out what is the angle between G and my world frame, x0, y0. And then there's a rotation matrix associated with that, and use that in order to transform. I'll use that because I would need that to later on when I try to take the gravity term in my equations. The gravity terms cannot be in the ramp frame, they have to be in world frame, because the gravity is going to push the robot forward, the G sine gamma pushes it forward. So the way I'll do this is the following. Let's take care of gravity. That's my ramp. Say this is gamma. Remember, my world frame is along the ramp. This is the ramp. But I need to keep track of the frame which is attached to gravity. So let's say that's the gravity frame, xg, yg, and gravity is along this. Okay, so I don't quite need the homogeneous matrix here. What I can do is, if given a position, let's call this R in frame 0, then I can relate it to the frame G, which is my world frame, through this rotation matrix. This is so cosine gamma minus sine gamma, cosine. Right, this is going back to some of the earlier derivation I did about how the rotation matrix is related between two frames. As long as you can identify the angle between x of one frame and another one, you can write that relation between the two. In this case, what I need to do, however, is everything is going to be in my world frame, right? Everything we've done so far is in the world frame. So instead of writing everything in gravity frame, we write everything in frame 0 or the world frame. And so what we need to do is we need to write R. So let's just call this R gamma RG. If I want to compute RG, then it will be R of minus gamma, or rather R inverse gamma. Right? What I did was I just multiplied both sides by R inverse. Now it turns out that if there is a rotation matrix, there's a property of rotation matrix that the R inverse is also the R transpose. This is R transpose of gamma. That's true because R transpose R is I. Okay, if you take the rotation matrix, take the transpose, multiply with R, you should get I. And because of this, R inverse is R transpose. Is that right? R inverse, yeah. You just pre-multiply both, or post-multiply both sides by R inverse, you get R inverse R transpose. And that's why I can write that. And so this would be RG equals cosine gamma. So remember, it's the transpose of this R, which I wrote down earlier. So I just need to swap the minus sign on the sign. Sine gamma minus sine gamma cosine gamma times R. Okay, now that we've got that, the velocity. So we got the position. That was the hardest part, I would say, by so far, and you'll see that's the only thing we need to really work hard on. Once we have that, everything else follows from the position vectors. So we need to compute the velocities. So velocity of any point is the Jacobian of that point. Okay, I put star because that star could be C1, C2, G1, G2, P, whatever you want, you can put there, but it's as simple as taking the Jacobian. In the language of Python, SymPy, you just say Jacobian, and then it'll give you the velocities. You don't have to anything. You just have to write the right. My bad, this is wrong. I shouldn't write this. It should be J star, which should be D of whatever that point is, dq, q dot. My bad, it should be like this, where this star is Jacobian of that point. So it should be the Jacobian of the position vector, and the position vector is something which we wrote down earlier, either C10 or G10, any of those. Okay, so you'll have to, of course, take the x and y component only. You can't take there's x, y, and 1, right? Ignore that. You just take the x, y, take the partial derivative, and then you have. Again, I won't do this by hand. It will all be done symbolically. Okay, that's step 1. Took the most time. Now it's pretty easy from here. Step B is the Euler-Lagrange equations. So here we write half m v of px square plus v of py square. So when you compute the velocity in this fashion, you'll have two components, the x and y. Take the x component, square it, take the y component, square it, and sum it up. That's the velocity for the point mass on the hip. Then we have a similar thing for the two legs. So vg1 x squared plus vg1 y squared plus half m vg2 x squared plus vg2y squared plus, so remember that the legs have inertia, and this angle is θ1. This angle is θ1 plus θ2, where this is C1, this is C2. So this is a leg. So the energy for the first leg is going to be θ1 dot square, because the angle made by that leg with the vertical is θ1. So the rate of change of the absolute angle is the velocity. And then for the other one, it will be θ1 plus θ2, θ1 dot plus θ2 dot square, because the angle made by C2 with the vertical is θ1 plus θ2. We need to take the rate of change of that and then square it. Okay, so that's the total kinetic energy. Then we need the potential energy. So here is where what you need to do is mg. You need to compute the position of the point. In this case, it's P. and you'd have to do it in global frame. Okay, so how do you do it in global frame? What we have done so far is we've computed the position in world frame. So P0, right? We've computed P0. If you want to compute position in global frame, this is the ground frame, then you need to use this transformation. So what you need to do is here, R of minus gamma or R transpose of gamma times P0. So this will give you P in frame G. So again, it'll have X, Y, Z. You only need to pick the Y component and put it there. Only Y component. Okay, similarly, we have M, small g, Y of say G1 in frame G plus M, G, Y, G2 in frame G. And you need to do something similar for them. Compute, so it will be R transpose gamma G10, R transpose gamma G20. Okay, so again, I won't do it by hand, I do it using SymPy, and I'll show you the code. Okay, and then the third step, Euler-Lagrange equations, which is d dt of dl dq dot minus dl dq equals, if I put that L, I forgot to write L. L is t minus v. Okay. Now all these things are equal to the constraints or the external forces. In this case, because we've used a floating base, you should have to account for the external forces which keep the leg grounded. Here, Q is going to be X, Y, theta 1, theta 2. And so what you need to do is you need to add to this what they call Lagrange multipliers, Y, C, C1, T of R, T of R, C1 with respect to Q plus lambda C2 lambda C1, lambda C2 are Lagrange multipliers. And then note that these terms are basically the Jacobian of C1 and the Jacobian of C2. So that's all readily available because we've already computed the positions of that. So these Lagrange multipliers are unknowns. Okay, and this is very, very generic, the way I've written it. In case of the specific system, so for example, in this case where those forces keep those points, C1 and C2 grounded, those Lagrange multipliers are actually the constraint forces. So another way to show it is, let's draw the legs. This is C1, this is C2. C1. Lambda C2. So those are the forces. Okay, so that's it in a very generic fashion, assuming that both legs are on the floor. Now we know that that's not true. C2 is always the leg which is in the air. C1 is the one which is grounded, right? So we know that this force has to be zero. It's not there. I just wrote it just to make it very generic, but it's not there. It's because the leg which is swinging is not acted upon by a force. So that is zero. So the only force left is the other ones. This one is zero. Okay, so what we do is we take these equations. Now, since you can see that Q has 4 degrees of freedom, those two xy, which are not there in the double pendulum, appeared here because we used a floating base. Turns out then you take the derivative, you have not 2, but 4 equations, just because of the floating base. And turns out that those 2 equations, the first 2 equations you get, which is something x double dot, something y double dot, are actually something which you use to compute those forces, unknown forces. Those are not really required for doing any simulation. So what we really need to do is we can actually eliminate the first 2 lines in those. There are 4 equations. The first 2 equations don't really have anything to do with accelerations. That's because, remember, this x double dot, sorry, x and y. Since this point, C1 is grounded, x double dot equals 0 and y double dot equals 0, right? It's not going anywhere, it's fixed. So those 2 equations basically give you an identity. It gives you the constraint forces. Let me write that down. In EL equation, first 2 equations, you can get lambda C1, which will have lambda C1x and lambda C1y. So you get those. For the third and the fourth equation, will boil down to something like this: A theta 1 double dot theta 2 double dot equals and then you can solve for theta 1 double dot theta double, just like what we've done for pendulum. So what I'm saying is that even though we started with a floating base, we did all those things, it actually boils down to the equations of a double pendulum, which are these, right? We had the same equations for a double pendulum. And so we can solve for theta 1 double dot theta 2 double dots.